Good morning, good afternoon, or good evening, ladies and gentlemen, and welcome to our very last unit of new material. That's right, folks. After we finish these next three lessons, we will be done covering new material for our class, and we'll be spending the last few days until May 29th basically just reviewing. Of course, there will be no final exam this year, but it's still a good idea to just go back and sort of review some of the material that we have covered throughout this semester. So, without any further ado, let's jump into it. This unit is all about waves. And of course, you're probably familiar with the concept of a wave. If you've ever been to the beach of some large body of water, then you've no doubt seen the waves of water washing in. But waves also refers to things like sound and light. So we'll talk about all of that stuff moving forward. Now, just a quick review before we jump into the main body. Remember, we talked about electricity and magnetism in our previous unit, and we learned that electricity and magnetism are two versions of the same force. In other words, one can cause the other. We also learned that forces can cause the transfer of energy from one place to another, and this was from several units ago. Alright, so these two concepts will become important as we move through the rest of this unit. So what is a wave? Well, in simplest terms, a wave is just a traveling disturbance that carries energy. What kind of a disturbance? Well, take a look at this picture of an ocean wave. The water is very clearly being disturbed. It's being lifted up and out of its normal position, and then it crashes back down into where it originally was. This is a disturbance. So a wave is just any sort of disturbance that moves. It can move through a material. Some types of waves can move through empty space, but something somewhere is being disturbed out of its initial position and then allowed to return. All waves are caused by vibrations. So in the case of ocean waves, it's caused by the vibration of the wind against the water surface. If you strike the surface of a bell, it causes a sound, which is a type of wave, and that's caused by the surface of the bell vibrating back and forth very quickly. Now, before we move any further, let's talk about what is a medium. And I don't mean like small, medium, or large. In this sense, a medium is just some type of material that a wave can travel through. Not all waves require a medium. Mechanical waves do require a medium. Mechanical waves are things like sound or earthquake waves. These are waves that have to move through some sort of material. They cannot move through empty space. So if you were in outer space where there was no air, you would not be able to hear things happening around you. That's what a lot of science fiction movies get wrong when they see a spaceship come roaring by or it blows up and you hear a loud kaboom. That would not really happen. If something exploded in outer space, you would not be able to hear it. But you would be able to see it because electromagnetic waves, which includes light, they can travel through outer space. So if a spaceship exploded in a fearsome space battle, you would be able to see the explosion but not hear it. And that's why we can see the light from the sun, but we cannot hear what the sun sounds like, which is probably a pretty good thing because if we could hear it, it would be deafeningly loud. A surface wave is just a special type of mechanical wave. It happens in a medium, but it happens at the boundary or interface between two media. So an ocean wave would be an example of a surface wave. Ocean waves really only happen at the surface of the water where the water meets the air. If you go down more than a few feet, the ocean waves don't affect you anymore. So this is a common diagram that you'll see of a wave, this sine curve or S curve. And I just wanted to use this diagram to illustrate a few of the parts of a wave. Now the top of each curve is called a crest, like the crest of an ocean wave is the highest part of the wave. And then the bottom of each wave is called a trough, T-R-O-U-G-H. If you live on a farm or you know somebody who does live on a farm, they may refer to the buckets that they feed animals out of as a trough. So you can think of that as like a little bucket where you could put some food there. Okay, so the trough is the bottom part and the crest is the top part. The distance between two crests is called the wavelength, all one word. And that distance is the same as the distance between two troughs because the crests and the troughs are evenly spread out. If you draw an imaginary line through the center of the wave, the amplitude is how high above or how high below that imaginary line the wave gets. So you can think of the amplitude as the height of the wave, and then the wavelength is the length or size of the wave. So let's take a look at this animation. We see a boat that is bobbing up and down on some passing waves. And also, some of the molecules of water in this wave have been illustrated. And we can see that the water molecules are really not moving along with the wave. They're just kind of moving up and down, but they're basically staying where they are. So the energy of the wave is getting transmitted, but the water molecules themselves are just moving up and down. And the boat that is riding the waves is also just kind of moving up and down. It's not really moving with the waves. And in fact, as we said, the ocean waves are surface waves. So if you go down a few feet, you can see that the molecules down here are barely being disturbed at all by the waves that are happening up here. So an ocean wave really just does happen in the top few feet of the ocean. So getting back to the concept of wavelength. Wavelength is abbreviated by a Greek letter lambda. So this is not an English letter. If you're like, oh, I don't remember seeing that in the alphabet, it's because this is in the Greek alphabet. And to make a lambda, you make a little swish, and then you give it a kickstand. All right, it's just a swish with a kickstand. Wavelength, as we said, is the distance between two consecutive crests. Consecutive means just one right after the other, or between two consecutive troughs. As we said, the crest is the highest part of the wave, the trough is the lowest part. Now the SI unit for wavelength is a meter. We measure the length of a wave using meters. Amplitude, we said, was the size of the wave disturbance, so how tall the wave is. And then one factor that we have not yet discussed is frequency. Frequency is abbreviated with a lowercase f. Now in some sources they will use another Greek letter called nu to represent the frequency of a wave, but we're just going to use f. And frequency is the number of waves that pass a given point in a second. It is measured in hertz, abbreviated capital H, lowercase z. So if a wave has a frequency of 1 hertz, all that means is that one complete wave, one complete up and down, will pass by a fixed point every second. And if you count the number of seconds, that's the number of waves that will go by. And if a wave has a frequency of, say, 2 hertz, then it means 2 complete waves, 2 complete up and downs will pass every second. All right, so to illustrate that concept, here are 3 different waves. The red wave has a frequency of 1 hertz. So this red ball that is generating the wave is bouncing all the way up and down once every second. The green wave has a frequency of 2 hertz, and the blue wave has a frequency of 5 hertz. Now notice that the waves are traveling from left to right. They're all traveling at the same speed. One's not moving faster than the other. It's just that the object generating the wave is vibrating faster for the blue one and medium for the green one and then slower for the red one. All right, so they all have the same speed, but they have different frequencies. Also notice that as the frequency gets higher, the wavelength gets shorter. These waves are closer together. So for example, if we look at an illustration of 2 waves, even if they're not moving, we can guess which wave would have the higher frequency, assuming they have the same speed. This wave has a longer wavelength. Its waves are spread out. This wave's crests are bunched together, so we would guess that this wave has a higher frequency. If both waves are passing by you at the same speed, this wave would be going up and down faster, and this wave would be going up and down slower. So this is the higher frequency wave because it has the shorter wavelength. Next, let's talk about wave speed. As the name indicates, it's the speed at which a wave moves. It's how quickly the wave transmits energy from one place to another. And just as we measure the speed of any other object, the speed of a wave is going to be measured in meters per second. Now, to calculate speed, we would normally take distance divided by time. And you can do that if you know the distance that a wave travels and the amount of time. But it's often easier for a wave to multiply its frequency by its wavelength. So for a wave, speed is equal to frequency times wavelength, f times lambda. Remember, lambda stands for wavelength. So let's take a look at a little practice problem. What is the speed of a wave if the frequency is 40 hertz, 40 waves per second, and the wavelength is 18 meters long? Well, we're given the information that the frequency is 40 hertz and the wavelength is 18 meters. What's unknown? We want to know the speed of the wave. We have a formula for that. Speed is equal to frequency multiplied by wavelength. So we will substitute in our numbers 40 hertz for frequency, 18 meters for lambda, and then we will multiply them together. You grab your trusty calculator. 40 times 18 is 720, and the units for speed is going to be meters per second. So this wave is traveling at 720 meters per second, which is pretty fast. That's more than twice the speed of sound in air. Next, what is the frequency of a wave? So now instead of trying to solve for the speed, we're trying to find the frequency. If the speed is 330 meters per second and its wavelength is 6 meters. All right, so that's the information that we're given. We're trying to find the frequency. Using our triangle, we would say that frequency is equal to speed divided by wavelength. F is equal to S divided by lambda. Plug in the numbers that we know. The speed is 330 meters per second. Wavelength is 6 meters, so plug in those numbers and divide, and the frequency of the wave is 55 hertz. Now there are several factors that affect how quickly a wave moves. One of them is how dense the material is that the wave is moving through, and also its elasticity. Elasticity is a term that describes how quickly a material snaps back into shape after being stretched out of its original shape. Also, the temperature of a material can affect how quickly a wave moves. The amount of energy that a wave carries is related to the wave's amplitude. That is to say, the greater the amplitude, the more energy is carried by that wave. So here we see two waves that have the same wavelength. All right, and we assume they're moving at the same speed, so they have the same frequency. The only difference between the two waves is that this wave has a small amplitude and this wave has a very large amplitude. So between these two waves, we would assume that the wave with the higher amplitude is carrying more energy than the wave with the lower amplitude. Waves have different shapes depending on what type of wave they are and what type of material they're moving through. The first type of wave we want to talk about is called a transverse wave. A transverse wave is the type of wave you may think of whenever you hear of a wave. It's a typical S-shaped wave. In a transverse wave, the medium is moving at a right angle to the direction of the wave. I know that doesn't make a lot of sense, but we'll look at an animation in just a moment, and hopefully we'll help explain it. A longitudinal wave is where the wave material is actually moving in a parallel direction to the direction of the wave. There are areas where the materials are getting squeezed together. That's called a compression. And then between the compressions, there are regions where the material molecules are being spread apart, and that's called a rarefaction. Kind of hard to say, rarefaction. Sounds like a car trying to start out, rarefaction. So let's take a look at these two types of waves and see if we can see the difference. We will start with a transverse wave. So as you look at this material, these little orange circles represent molecules of the material, and you can see that the wave is moving from left to right as it moves from left to right across the screen. But as the wave moves from left to right, the materials, the molecules, move up and down. And I made one of them red just so you could more easily track the motion of this particular molecule with your eye. So the wave is moving from left to right, but the molecules are moving up and down, which is at a right angle to the direction of the wave's movement. This we call a transverse wave. Now here is a longitudinal wave, and you can see that again the wave is moving from the left to the right. This time the molecules are also moving from left to right, and as they do so, there are areas where the molecules are getting squeezed together. Those are the compressions, and then between them are areas where the molecules are getting spread apart, and those are rarefactions.